That's a nerd here.
Billy, no!
Sorry for that. That was my friend. Anyway, we're gonna go over some of the problems that I promised you guys I would do on Saturday, but unfortunately, it takes a lot of getting ready to get these videos together. So what I'm gonna do is and by the way, this is for you AP1 guys. AP2 if you guys want to just look at it. And anybody else on the internet that just wants to know how to solve some physics problems, this is for you guys. Anyway, so what I've done is I've solved in, just my textbook I'm using here, College Physics, Chapter 3. I've solved questions 1 through, I believe I went to 25. I went through 25. I didn't do the last two, and let's spend like the end. But 1 through 25, odd, right? Because I guess it's the answers. It doesn't really tell us how to do any of it. So that's what I'm here for. Anyway, first problem. I'm going to just jump into this. I'm going to take it nice and slow so everyone who knows very little can get it, and everyone that's like really advanced, feel free to skip ahead throughout the video as you need. Anyway, problem 1, chapter 3. This is the problem section, not the conceptual or any of that. Anyway, problem 1. Let's put it over here so you know which one I'm doing. And if you need to fast forward, see that number right there. Okay. Problem 1. Get rid of these goggles. An airplane is in a holding pattern. It flies at constant altitude, so it's at the same height, along a circular path with a radius of 3.5 kilometers. So, number 1 physics rule we always like to follow. Draw a pretty picture. And that's not it's supposed to be a circle, but it's not, obviously. But it's a circle. Everything's just squashed, right? Anyway, and it says it's 3.5, I think kilometers? Yes, 3.5 kilometers. Okay, now, you're going to see why in a minute, but this is going to end up becoming 3.5 times 10 to the third meters. So you can rewrite it like that right at the beginning here. And the reason is because we're going to be dealing with meters per second at some point, and we want everything to be in the same units. Anyway, and the book also puts the answers in there as well. If the airplane rounds half the circle in 1.5 times 10 to the 2 seconds, what a weird way to say time, right? T equals 1.5 times 10 to the 2 seconds. So that's our time, which is just what, 150 seconds? About. Okay. Right, is that right? Yep, 150. Determine the magnitude of its displacement. Okay, so first question, displacement. I'm not going to read the other ones yet. Well, this was tricky. I actually went through and solved for the other problems and then realized what they meant by this. Displacement just means, okay, from your starting point to your ending point. Okay, well, according to the problem, it says they did a half circle. So let's just get rid of this top one right away so we don't get confused by it later on. Half circle, well, if you talk about the displacement from here to here, not the distance traveled. So if we wanted the total distance traveled, we would take the entire curve here. We would need the circumference, right, of the circle. Well, it's talking about displacement, which means from point 1 to point 2, point A to point B, right? So that's just 2 times that, which gives us, was it 7 times 10 to the third meters. This is sort of a trick question, right? That's the answer though. It's just double the radius to give us 3.5 plus 3.5. Too simple, but they're just basically testing the definition of displacement at this point. Let's go with B. Since A was so easy. B is average velocity during this time. Let me move my book. The chair over here so I don't have to keep hiding from you guys. There's not like some secret thing over there that's telling me how to solve the question. This is actually the secret thing that tells me how to solve the questions, but that's something I spent half the day doing already. All right, so part B, okay, is average velocity, okay? Well, average velocity, from what I know it as, is, it's the average. So one thing we need to remember is we cannot include, well, let's just go along the path here. We know that we went this way for a while, and there's some curving and stuff, and we went this way for a while, and there's some curving and stuff. Okay, right off the bat, you should see that our up and downs are in opposite directions. And when we're dealing with velocity, we care about direction. That's average velocity. So if you guys remember the problem from chapter, I think it was 2, we were on a boat, we went across the lake and we came back and we asked for average velocity and it turned out to be 0 because they're in opposite directions, and when you add things in opposite directions, they become 0. Same with here. The entire path downward, any part that was down or in the y direction could be 0. So what we can say, all parts that were up and all parts that were down total to 0. All we care about is left to right. And what do we got here? That's still that 3.5 2 times over. That's still this number from up here, 7 times 10 to the third. Okay, now that's just so 7 times 10 to the third. Okay, that's just the distance, and that's meters. Okay, another way to think of that is 7 kilometers, right? But they don't do that to us. Okay, 7 kilometers, and then what do? We just divide by the time. 1.5, this is our t, 1.5 times 10 to the second power in seconds, and that simplifies to the average velocity, which is 46.67. Now here's a proof. This problem's a good proof. By the way, that's meters per second, right? Meters over seconds. Okay, this is good proof that an average velocity is not the same thing as an average speed. Speed, we don't care about direction. Speed, we only care about, we care about the entire path. And because so even if let's say we did this, and this was our path, and we just went all over the place, for speed, we would actually calculate every piece of here. For velocity, any up and downs and left and rights that were in opposite directions would cancel out from each other. So just keep that in mind as we go on here. All right, so speed, there's no canceling. Directions is not important, so all we care about is adding up the total path. Okay, well, if we know the equation for a circle, this helps because we know that to travel this half circle is half of the circumference. And the equation for circumference is 2 pi r, which is kind of silly because you see you have 2 and r. Well, 2r is diameter, right? Just doubling this radius. So it's pi times diameter. Okay, but then here's another problem. We only want half the circle, right? We don't want the whole circle. So we're going to divide by 2. Well, if we're dividing our diameter by 2, what do we get? We're back to our radius we started with. So actually, it's pi times radius. And that's just because it's a half circle. If it was a full circle, it'd still be 2 pi r. But because we're dividing by 2, we get rid of our numbers, and we end up with pi r. Okay, now that's the distance. Same thing, we're going to divide that by time. What's the radius? 3.5, so 3.5 times 10 to the third. Okay, so if I get my handy dandy calculator, can you pause that real quick? Hey look, it's like I never even left. Handy dandy calculator. And once again, we're just doing pi times r, so we can get the distance. And of course, we're not actually looking for distance, we're looking for speed. So once we get that distance, we will divide by the same time. Time isn't a vector, right? Time doesn't have, it has a direction, which is usually forward. That's weird, which is forward. But yeah, so that's pi times 3.5 times 10 to the third. Gives us 10,995. That's a big number, right? Okay. Why is that such a big number? That's right. Okay, and then what we're going to do is we're going to divide by our time, which is 1.5 times 10 to the second, divided by 1.5 times 10 to the second power, and that's going to give us 73.3, right? So that is a very, very different number. I'll write that in different colors so we get the answer here. We're going to get 73.3 meters per second. So you see, average speed was very different than average velocity. And of course, the reason was in average velocity, those opposing directions, you can't, they cancel each other out because you can add in one way and then you have to subtract in the other, right? We have one, we can decide this one's positive and that one's negative. And that's why they disappear. But we only go left to right. Now, if we did the whole circle, let's say we finished the whole circle, the answer to this would actually be 0, right? Because we would actually be canceling out everything every time we did a circle. The average would be 0. But they're tricky in this problem where they say, hey, we just want a half circle. All right, well, I think we're ready for problem 3. I went from 1 to 3, but like I said, we're doing odds today. All right, there's my blue pen. let's erase all this. Goodbye, problem. You will be missed. I shed a tear for every problem. I have to go erase off the board. I put a lot of heart and soul into these. Problem 3. You're going to be a purple problem. All right. Yes. Color is important. All right, problem 3. A miniature quadricopter. I think I call that a drone, but there is a technical difference. So I won't get into that. It starts arguments. A miniature quadricopter, not quadrilateral, quadricopter is located at xi of 2. So right off the bat, I noticed that they're going to want us to deal with xy coordinates in this. X and y. And it says xi, which we all know means x initial. It's going to be at 1, 2. So this is 2. And it's going to have a y coordinate. I think I'm right. Remember this one from earlier? 4.5. Yep. So 1, 2, 3, 4. And we'll say that's 0.5. And we'll go over, we'll put a dot for both of those. Remember, that's 4.5. Cool. That's the y direction. What do we got now? Now it says at time 0. So this point is t equals 0. This magical starting point. All right. And it moves with an average velocity having components v. Now this is really weird how they write this, but they do write v a v of x. Okay, I don't like that. I'm going to say v of x. That's simpler to me. For some reason, write all those other little subtexts. V of x of 1.5 meters per second. And we have a v of y of -1 meters per second. Cool. And let me guess, it's going to say, yep, what are the x and y coordinates at t equals 2? So A is x coordinates, problem B is b coordinates. So you could sit here and try to do a bunch of complicated math. This problem is oversimplified, or just really, really simple. So it's just saying that, hey, after 1 second, what's my x going to be? Well, it's going to be 1.5 less. And after 2 seconds, what's it's going to be? Oh, sorry, not less, more, right? Because it's positive. Let's keep that in mind. This is positive. It's going to be 1.5 more. So we'll be at 3.5. Be right here. And then 1 more second. So remember, it says what's happening at t equals 2. That's what we want to know. And at 1 more second, we're going to go another 1.5. So that'll be 4. That'll be 5, right? So at this point, x should equal 5 meters from the origin, right? Not from our starting point, from the origin. Okay, because we actually start in this weird spot. Our origin is actually 2 comma 4.5, as you can see from our graph here. Anyway, y value, y is actually getting smaller. So we go from 4.5 in the first second, down to 3.5, down to 2.5. And guess what, guys? That is the end of this problem. 2.5. That's it. That's the solution. Like I said, it's just a thinking problem to make you think in terms of a graph instead of thinking in terms of straight. It's like, hey, let's go from real world scenarios to purely graphical scenarios. Anyway, so let's erase this. Everyone see the answer? Good to go. We're going to go to problem 5. Okay, this one didn't deserve a lot of time. This one I'm a little happier to erase. Still, tear. Anyway, problem number 5. Where are you at? There we go. Ooh, this is an interesting one. I think we have some vectors going on in this one. Maybe, maybe not. A car is traveling east at 25 meters per second. East is this way. At least on my, if we pretend this is north, south, east, west. Actually, it is east in the real world too, compared to where our house is. Anyway, problem 5, 25 meters per second. That's supposed to be a 5, buddy. 25 meters per second. And then what? Then it says, then we accelerate to 35 meters per second due north. Now this one took me a little bit. Now this is not an acceleration, it's a speed. But because we're going in a new direction, we still call it an acceleration. Changing direction is the same thing as changing speed in physics. It's an acceleration. If I'm going 10 miles per hour north, and then I turn and go 10 miles per hour northeast, that's an acceleration still. We are changing directions. And the reason here is we're changing actually a 90-degree direction. Now, what's interesting about this is it ends up being, I believe, a vector problem. Yep, that's what I got. So here's how it works. And I think that the key word here is calculate the magnitude of the average acceleration. There's that word average again. We're not looking for a specific, like, what was the acceleration over the whole time? No, we're looking for what was the average from when it started turning to when it turned. Okay, so that's the trigger word, average. Remember, every time you hear the word average, so let's do average acceleration, right? We hear that. I'm going to change colors here so we can see it a little better. That means total change in velocity. I like adding the word total in there. Over total change in time. You guys probably remember this from the last section when we did that. We did a problem where we took a trip and then we took a lunch and then we continued the trip and we had to include that break period as part of our average speed. Okay, it's the same idea here. We're going to do all totals here. Well, in this case, what's the total? Well, 25. Well, you know what? Let's simplify things. Can we really total something horizontal and something vertical? Well, yeah, but we have to decide, we have to give it units. So what we're going to do is we're going to call this X. We're going to call this Y, just because we're horizontal and vertical. We don't have to. You could do this without doing that, but it makes it look prettier on paper, right? So this means, what's our total velocities? We have a velocity in the X direction, this one, and we have to add that to a velocity in the Y direction. And then we have to divide that by our change in time. Now, velocity in the X plus velocity in the Y. Okay, immediately, if these are in opposite directions, you know that we're going to be dealing with some sort of Pythagorean theorem, some sort of trig maybe. In this case, adding an X to a Y is just what we call the head to tail method. We do this, and if we can figure out this length right here, that is literally the combination of this and that. Okay, so let's figure out what that is. That'll be, so in our calculators, what we'll write, okay, we'll call this R, this third side. We like to use R because we like to do things in circles, radiuses, but don't worry about that yet. So R equals the square root of 25 squared plus 35 squared. Remember, the way I got this is I just took the whole a squared plus b squared equals c squared to find this third side, and I got rid of that square by square rooting it. So that's why it becomes this up here. This becomes that, just in case you're wondering where it came from. All right, cool. So let's run this in our calculator really quickly. Now, the nice thing about this question is they don't actually expect you to find a vector. They specifically say the magnitude. The magnitude means we're just looking for a number. We want to know how much it is. We don't care the direction. Now, we all already know the direction. It's somewhere northeast pointing. And if we really want to know the direction, we'd actually use some trig to figure out what this angle is. It's opposite over adjacent. But this problem doesn't call for that, so we're keeping it simple. Okay, let's clear this. Second, square root 25 squared plus 35 squared gives us 43.01. And is that what I got on my paper when I checked myself earlier? No, I didn't. I did something wrong. Let's try that one more time. Oh, I think it's a bracket issue. Square root of 25 squared. Oh, I get it. 25 squared. Let's go back. 25 squared plus 35 squared gives us 43. Oh, no, I didn't do it wrong. This is right. This is the right value. This is the correct value. I just forgot I haven't divided by time yet. I was like, my final answer is not that. So we get 43.01 about, approximately, meters per second. Now, this is what threw me off. We're actually looking for acceleration, right? So it should be meters per second. And the way we get that is we divide our change in speed, which is this combination, by our time. And what was our time? They gave us the time, right? Oh, all this happened during 6 seconds. Okay, if I didn't read the problem at the beginning, let me do it right now. By the way, this was problem 5. See, I'm already breaking my own rules. I said I'd write a number up there. It says a car is traveling east at 25 meters per second. When it turns due north and accelerates to 35 meters per second, all during the time of 6 seconds. Calculate the magnitude of the car's average acceleration. So we have a time of 6 seconds. Well, we'll just divide this by 6, and I believe we get 7 something. 43, you can kind of tell that just by looking at the numbers. Divided by 6 gives us 7, so we get a acceleration of 7.168. You know, you can keep going, but this is good enough. Okay, and that's meters per second squared, or meters per second, right? Cool, that's an acceleration. Change in speed, remember? All right, so let's bump it up. Problem 7. This one was nice, but you know, if it was like a real complex problem, like something we'd see in a normal test, we would actually have that angle added in there. But like I said, this is just the beginning of the section. So we'll go to 7 now. All right, problem 7. And we'll go to light blue this time. I like light blue. And problem 7 states, okay, a student, this one we did in class a bunch. Did it twice, but we'll do it one more time on film, or on video. Film's like ancient, right? A student stands at the edge of a cliff and throws a stone horizontally. Boom. Throws a stone horizontally over the edge with a speed of 18 meters per second. So, 18 meters per second. And the cliff is 50 meters above a flat surface. This is our flat surface. Okay. Horizontal surfaces. What are the coordinates of the initial position of the stone? Okay, now this is a little weird, but all we're doing for A is saying, okay, what's the X and Y value here if we pretend this is our starting point? And actually in the picture they put here, they put the letter O here, and that just stands for origin. So we know that's where we're starting. Well, in the X direction, we're at the origin still, in the X direction, so we'll say it's 0. And so I'll write X equals 0, and Y, that's supposed to be a semicolon-ish, let's make it a little more. And Y equals, well, 50. Pretty simple, right? And those are meters. Okay, sweet. Let's do part B. That was simple enough. Part B. What are the components of the initial velocity? Okay, this problem, what they're doing to us is they're having us write each part of the equations we're going to use to solve like part D and E, oddly enough. So the equation for velocity in the X is velocity equals distance over time, x over t. But fortunately for us, they've already given us the velocity in the horizontal in the X. It's just 18, so we'll just write that equals 18 meters per second. We already got that one. V of y, on the other hand, we don't have. And we know the velocity in the y direction is acceleration times time, which, now, a lot of you see anything with y and you're like, oh, that's the y equals 1/2 at squared. No, that's only for distance. We only, if we're just looking for a velocity, just keep in mind that it's just, I'll put a delta to make it easier. Delta v equals a times t, which we know a in this case is gravity, so it's 9.81 t. There's that equation. Okay, let's go to part C. See, we're just setting, see, get it? But see, we're setting up the equation here. We're setting up all of the equations we're going to need to solve the last part. C, write an equation, just what I thought. X and Y coordinates. Well, what is X? X, position, so if you want to know the exact position, we're going to use, this is our starting position. Remember, don't confuse these. This is starting position, so I'll write I for these, so we know. This is the position at any time. Let's come up with an equation that I can, if I want to know its position anywhere along its path, I can figure it out. And the equation for that is going to be x equals, well, it's just rearranging this top one, v of x times t. And once again, that is 18, but I'm going to add the times t because this was our starting velocity. This is where we're going to be all along, 18 times t in the x. Cool, so we'll circle that. All right, now for the y direction, okay, this is where we're going to use our y position and acceleration formula. So we're going to say y, well, I'll write the whole thing. Delta y equals velocity in the y times time minus, now you're going to ask yourself, why are we using minus? And I should have used it here too. Well, I decided since this was 0 and this was 50 at the top, so I'll write 50 right here, 50, and this is 0 down here, that down has to be negative. And gravity is pulling down, so gravity is negative. So in this equation, we actually usually write 1/2 at squared, but because a is actually going to be gravity, and we would add that, because a is gravity, we're going to make the whole thing negative, because we know that it's going down. And you'll understand why that is, because it's going to be good if we threw something up, then that. All right, so, oh, you know what I did wrong? I did something wrong. This is wrong right now. Well, we'll come back to it. This is the equation for velocity at any point. But our starting velocity, our vy of I, is equal to 0, right? Because as we throw this off the cliff, they specifically state it's horizontal. At no point are we throwing it in the air or throwing it down. There's no starting velocity. Now, after like a millisecond, of course, or even less than that, obviously, there is some speed in the downward direction. But at the beginning, there's none. So what happens is this entire chunk, because that is 0, well, we know 0 times t, or anything times 0 is 0, it goes away. Cool. Now let's break apart this delta y really fast. Okay, delta y is the same thing as saying y final minus y initial, and it equals those things. Well, do we have a y final? Sure we do. It's 0. When it lands, the last y coordinate we're going to have is going to be 0. And actually, let's just draw the path real quick so we see that. We don't know what the x is. We don't know how far out it's going to be, but we know in the y, the up and down, this is 0. So because that's 0, y final becomes 0. Okay, and look what happens. We get 0 minus y initial equals negative 1/2 gt squared. Well, once again, we can get rid of the negative on this side if we get rid of the negative on that side, right? We're just dividing by negative 1 on each side. And there we go. We got an equation now. And, well, we're not done yet because we have g. Well, what can we do with g? We can plug it in. It's 9.81. What's 1/2 of 9.81? It's about 4.9. 4.9. I love this equation because if we know time, we can find out how high something was dropped. Or if we figure out, if we know how high something's dropped, we can figure out time. In this situation, we know how high it's dropped from already. So this actually becomes 50, because that's 50 high, right off the bat. So you can see this equation becomes something really usable really quickly. Now in the problem, it does say write the equation, so you could just leave this as y equals, but I'm skipping ahead. I know this is going to become that eventually. If not, the equation would be useless, right? Because we already know this number. We're not trying to find it. All right, next piece, D. Write the equations of the positions of some stone with time. Okay, that's what we did. Sorry. Part E. Here we go. Finally, we get to do some work. How long after being released does the stone strike the beach below the cliff? Well, what did I just say? It's saying time. How long does it take to go from here to here? Well, we've got time in a couple equations here. We got time here, right? Right, we got time here, velocity here. But we don't want to use this one. And we can't use time in this equation right here because we don't know what that is either. So we don't know what it is after time. So it's easiest if we use this equation to solve for time, right? And if we all remember from class, if you rearrange this and solve for time, you end up with time equals the square root of y over 4.9. And in this case, y became 50, right? We know what y is in this situation. It's 50. Well, let's do our handy-dandy calculator here. Handy-dandy notebook. No, handy-dandy calculator. Not getting sued today, no. Square root of 50 divided by 4.9 gives us, boom, 3.19. Okay, now, this is going to be important. So t equals 3.19. I'll draw a little thing around it. The time is super important on this one. Now, when I was in class, I said the textbook was printed wrong. That the next set of answers we're going to get were impossible with the information we got. I was wrong. I sat there and I worked on the problem today, and I realized we weren't doing it right. There was the wording was just a little bit off enough in the textbook to make me realize what they're really looking for. But anyway, we just solved part E, which gave us the time. That's how long it took for this to fall. And it's really predictable, right? Because everything that falls at 9.81 meters per second. And as long as we know how high it fell from, we can figure out how long it took to get there. And vice versa. If we knew how long it took to get there, we can figure out how high it was falling from. Okay. Anyway. So in this class, I usually liken it to like Timmy falling down the well. You hear Timmy fall down the well, you hear it splash, the amount of time it took him to hit the bottom. If you can know that time, you can figure out how high up you were, how much rope you need to get to save Timmy. Anyway, and they must have a lot of wells back then. So last part says, with what speed and angle of impact does the stone land? Now, I look at my notes on this because this took me a little while to figure out myself at first. This problem 7. All right, here we go. So, one thing I didn't think about is, I assumed right off the bat that this impact was straight down. I was like, it curves for a while, then it comes straight down. But that's not correct. Because it's coming forward, there is some slight angle here on the ground. And it's like, okay, well that's fine. If that's the one we're looking for, how do we even find that thing? It doesn't make any sense. There's no thing. Well, it does make sense. It makes perfect sense, actually. And the reason it makes perfect sense is we have to take, instead of me just saying velocity in the y to figure this out, which is what I thought I needed to know, I actually need to know velocity in the x and add it to the velocity in the y. And what we'll find is that these are, because they're two different values, we'll end up in fact getting an angle of impact. And you'll see, we'll build a triangle out of it. Okay, velocity in the x, we know what that is. That's 18 meters per second. That didn't change. Okay, remember that's a rule. If we throw something straight out, as long as there's not a lot of air resistance, the speed that it's moving forward is always going to remain the same until it hits the ground. Now, of course, when you drop something, the vertical speed is continually changing because of gravity. Gravity doesn't work this way. So everything that's moving this way, it's going to keep moving this way at the same speed, even while it's falling at 9.81 meters per second squared. Okay, so let's do this. V of x, we know is 18 meters per second. Now what's v of y? Well, we got to plug in some values to figure that out, don't we? Well, if I want a velocity in the y, I just take acceleration times time. Well, we now have a time, don't we? So our acceleration is 9.81 again. Gravity, 9.81, and we multiply that by time, which is 3.19. And we get 31.29. So, and that makes sense. This made the same. This, by the time it hit the bottom, was going 31.29 meters per second. Okay, what does this mean? This means we have an x and we have a y vector. And if we want to know the combined velocity when we hit the ground, we have to find that third side. So 18 and 31.29. Like I said, this is not something I expected, but after reading a couple times, I was like, oh, you know what? They're looking for the total velocity, not just the, because they don't actually say the velocity in the y. I think the word they used was with the speed and angle of impact, or with what speed, that's what got me, and angle of impact does the stone land. I was like, they want it all combined. So let's figure this out. Okay, just like the previous problem, to figure out the third side, I'll call it r again, we'll take the square root of 18 squared plus 31.29 squared. Get my calculator out one more time. Okay, second, square root of 18 squared, I made this problem, plus 31.29 squared gives me 36.09. Okay, so that means the velocity here was 36.09, or we could say here 36 0.09 is the length of that vector. Okay, so it's some x and some y. But what's the angle? What angle is it hitting that at? Well, that's easy. We have 3 sides of a triangle. We can pick any side we want. Just because I am in the habit of doing it, I'm going to use tan, opposite over adjacent. So I'm going to go tan inverse equals, or tan inverse of theta, no, tan inverse equals 31.29, oh man, my math's way off today. So tan inverse of 31.29 divided by 18 equals our angle, right? Whatever that angle is. And just remember, that's because of the rule TOA, opposite over adjacent. Okay, so, sorry, sometimes I ring like that. It was Colby. Square root, oh no, tan inverse, geez, see, I'm way off today. Tan inverse of 31.29 divided by 18 gives us a magical 60.08 degrees. Hey, those of you who were in my class and we figured this was impossible, remember the answer? It was 61 degrees. I was wrong. We were all wrong. There is a way to solve this. This is what they were actually looking for. So, we'll just say 60.1. Match the book, right? There we go, part E. This problem had A, B, C, D, E, F. This was actually part F. F parts. Or 6. F's not a number. 6 parts. It's like, how many numbers did you do today? Well, I did F of them, Bob. It's like, that makes no sense. Well, you're not in physics. Physics isn't meant to make sense. Except for, it does. It does make sense. Can we erase all that? No, I'm just kidding. Anyway, let's go. Problem 9. I didn't label it again. By the way, that was problem 7. You see that for 10 seconds, and then I'm going to erase it. We're now going to problem 9. I need to label that in the video in the bottom or something. We'll see what I can do about that. I'll probably forget, and then people will be like, I went to problem 7, and it was at the end of the problem. And I thought it was the next one. It was so confusing, Mr. McLeod. They say, the world is a confusing place, student. The world is a confusing place. Whew. This lab coat is getting warm-ish. All right, problem 9. Here we go. Marathoning all the problems. Mr. McLeod's crazy, right? Okay, the best leaper. I didn't realize there was a chart, but apparently the best leaper in the animal kingdom is the puma. Okay, ever watch Red vs. Blue? They say pumas don't exist. Pumas exist. They're real animals. They're not like the chupacabra. Anyway, the best leaper in the animal kingdom is the puma, which can jump to a height of 3.7 meters. This problem is an algebra nightmare. Just let me know. And you'll see why. So, it jumps at some angle. Actually, I think it gives us the angle, right? Yep. Jumps to 3.7 meters, so that's the height. 3.7 meters. And I'm probably going to go to my notebook for this a couple times, because walking through this and making mistakes over and over again on camera, it's fine. Just keep in mind, it's okay if you had to do this a bunch. And this is 45 degrees. So a puma jumps from the ground at 45 degrees. Not a puma, I guess this is the average. But there's something tricky here, and the problem is you have to know that the angle of 45, whatever, let's say I break this into x, y vectors, which we will do in a moment, x and y. The magical thing about 45 is it's half of 90, so x actually always is going to equal y in this situation. The magnitudes, the amounts are going to be the same number. And you got to use that piece of information to solve the rest of this. The fact that these are the same number, and the only way that works is because of the 45. Keep that in mind. Because it's half in the x and half in the y. 45 is half of 90, right? Okay, so I'm going to get my paper out for this one so I don't make a million mistakes in front of everybody here. Probably happened anyway, but it's alright. Okay, so this is what we do. This is what I did. First, I went and I said, okay, I'm looking for, what am I looking for? With what speed must the animal leave the ground to reach the height? So I'm like, okay, I gotta come up with some velocity. Initial velocity, here. I need VI here. Okay, and so I was thinking about it, I was like, well, I know that velocity equals, and I'm like, okay, it's jumping up, so I gotta deal with acceleration. So velocity equals acceleration times time. Well, here's the problem. I have two unknowns. of a t and a v. So I'm like, well, I also know that I can find time in the air using the equation y, so this is distance, we have that value, equals velocity initial, which is what we're looking for, times time, minus 1/2 gt squared. And I'm like, okay, well, we still have two unknowns, right? I have now v and the y, which I know is the cosine of that the sine of that angle with something I don't know still. So we're still dealing with so many unknowns. And then I thought about it and I said, you know what? If I can get rid of one of my variables in these two problems, then what I can do is I can solve for the other one. So what I did is I realized if I actually want to know what velocity in the y is going to be, I need to replace time in both of these, because there's really no way for me to find time accurately here. So this is what I did. I just took this equation and I rearranged it. Velocity over acceleration. And we'll just change it to g right off the bat, just so we're not confused when it's a big mixture of things. Velocity divided by gravity equals time. Remember, this is in the y. Equals time. And then we're going to plug this piece in everywhere we see time in this equation. Okay, we're just going to plug and go here. So y equals, this is getting a little weird for a little while, v of y times time. Well, let's replace time right off the bat with this. V of y over g, and I'll put that in parentheses, minus, now I made this mistake at the beginning. If you don't put a minus here and you put a plus, things end up wonky and you don't get the right answer. You gotta remember gravity's down. So even though we're just messing with variables, we still gotta think of it, the fact that it's negative and going down. So minus 1/2 g t squared, right? So t, which is vy over g, this is now t, right? Squared. Okay, probably notice right off the bat there's a lot of ways to simplify this problem, right? So it becomes y equals, well, vy squared, because vy times vy squared, it's still over g, minus 1/2 g times vy. Well, let's simplify this part first. Let's get rid of the square up here and put it into both of these. We're allowed to do that. Vy squared over g squared. Okay, we have g over g squared. So this g goes away, and the squared goes away. Okay, you probably see what I'm doing here. I'm trying to get the same units in both. Now, it's 1/2 this, once we simplified it, vy squared over g. All right, cool. Well, as you notice right away, we have this is the same as this. So we can actually reverse substitute and pull it out. So we do that, and let's go way over here. Rewrite the whole thing again. Y equals vy squared over g. Now, if we pull that out of here, if we divide this by itself, it becomes 1 minus, if we divide this by itself, because we pulled it out, it becomes 1/2. Look at that. We're getting a lot closer to a solution, right? Now look here real fast. Let's make sure we did it right. This multiplied into that and becomes that, right? We agree with that. And this multiplied into this became this. And this all came from the substitution when we plugged this into there. So we're still good. All right. Just making sure we're all right. So 1 minus 1/2, we're just done with numbers here, ends up just being 1/2. And I'll replace it with 0.5, just so it's easier to do with the math. And g, as we all know, is 9.81. And remember, we're looking for velocity, right? Well, do we know what y is? Do we know our height? Heck yeah, we do. It's 3.7. So let's just plug that in. And now what do? We got one variable left. That means we can solve for our initial velocity in the y. Now keep in mind, that's the y, that's not the x. But once we get it in the y, the rest of it comes pretty easily. So let's erase all this other math I did and finish solving this problem. So first thing I'm going to do is I'm going to move the 9.81 underneath the 0.5. You can do that because this is multiplied, so it's all one fraction. So 0.5 divided by 9.81 gives us a really tiny number. Remember, it's like 0.05 or something. 0.5 divided by 9.81 gives us, 0.051, let's say. This becomes 0.051. 0.051. And we'll do 3.7 divided by that to bring it over there. So 3.7 divided by, sorry about that, 0.051 gives us 72.54. Okay, and of course the last step we need to do is take the square root of that number, right? So square root, to get rid of that square, of 72.54. So I'll just do second, hold on one second, yep, second square root of that answer I just got, which was the 72.54, gives me a velocity in the initial of 8.51 meters per second. And look at that. We have an initial velocity now. Now, let's look over here. And let's make sure we got the numbers we're looking for. Make sure I'm not missing something here. 9. With what speed must the animal leave the ground? Okay, so that's in the y. So in the up and down, we are at 8.51. Okay, well, what are we in the horizontal? Okay, well, we have initial velocity, so we can actually figure that out pretty easily now using this equation right here, Vy equals g times t. So v of y, which is 8.51, 1 divided by 9.81 will give us the time the puma was in the air. Okay, like I said, this is just a long-winded algebra problem. The physics are pretty simple, but the algebra is a little bit annoying. 5.1 divided by 9.81 gives us a time of about 0.86. Make sure I'm on the right track here. Not just losing my marbles. I didn't actually write those numbers down, but everything looks right so far. So we have a t of 0.86. So far we got this piece of information. We've got this piece of information from all of our math. Actually, that's right here too. But all right, so we got those. Well, if we have a time, we can definitely find a velocity in the x, right? Okay. So, velocity in the x equals, x equals velocity times time. Okay, and what's our velocity in the x? Oh, we don't know the velocity in the x, do we? Oops. Let's skip the step. Sorry about that. I forgot the golden rule. I forgot it right from the get-go. Hey, what did I say at the very first step? I said because we're dealing with a 45-degree angle, velocity in the y has to equal the velocity in the x. Because the other half of this is also 45. And if you test this on your calculator, if you take a number, let's say I took the cosine of 45, I would get this number. And if I took the sine of 45, I would also get that number. I get the same number because it's a 45-degree angle. That's the part I'm missing here. So, in the x,
forgot to write number 9.
8.51. Get that every time. 0.51. If you can remind me, that'd be great. Times 0.86 is going to give me my velocity. Ooh. Yeah, it's going to give me my x. Do I even need this then? No, never mind. I was trying to find the distance there. No, we got 8.51 in the velocity in the y, and we got 8.51 velocity in the x. So you got to remember what we're looking for, right? We're actually looking for the combined velocity to say the puma's starting jump speed, right? So, well, we're going to take, we're going to do some Pythagorean theorem. We're going to go, okay, we have 8.51 in the y and 8.51 in the x, and we're just looking for this distance right here, and that'll tell us basically the combined velocity of the two vectors. So we'll do that real fast. We'll go second square root 8.51 squared plus 8.51 squared gives us 12.03, and that is amazing because that is the answer. 12.03 meters per second. I said, very hairy problem in the algebra sense, but that's the answer. And we're there. We made it. Okay. We'll do one more problem, and then we'll take a break for a few minutes, and then we'll come back. Sound good to you, Colby? As you see, I lost the lab coat. It's really warm in here. It's really cold outside, warm in here. We have an insulated garage / little office area, so that's cool. Anyway, this is going to be problem 11. See, Colby, I'm going to write the number up here.
Good job, Scott. Good job.
He's been waving at me like, number. Yes. This is problem 11. Anyway, I helped a couple of you during my AP night that some people came to, solving this problem. So, a place kicker must kick a football from a point 36 meters from where he's at, so 36 meters, and from the goal. Half the crowd hopes the ball will clear the crossbar. That makes sense. I mean, I wouldn't say it's exactly half, you know. If it's a home game, most likely more people are going to be there from where the game's at. But whatever. They hope it'll go over the crossbar, which is 3.05 meters high. Meters. Cool. So we have an elevation. We have a distance. This is our kicker. What else do we know? Okay. When kicked, the ball leaves the ground with a speed of 20 meters per second. You know what I love about physics problems? Is we do this and we're like, this guy kicks a ball, it's going 20 meters per second. First of all, how do you know that? You have to look like a computer. And then I say, hey, is it going to make it? And you know, if a real person in the stadium would have already known if the ball actually made it or not, and the time it would take someone to solve this equation. I think that's funny. It's like, will he make it? It's like, I don't know, watch the game. We'll find out. But it's physics. We're working with hypotheticals here. In this situation, it'd be like if I said, hey, kicker, if you kick the ball this hard at this angle, what will happen? And yeah, anyway, you'll see. This is at 53 degrees, I believe. Let's see. Yep, to the horizontal. That always means it's up above the middle. By how much does the ball clear or fall short of clearing the crossbar? Now, there's one major flaw with this problem. You assume in the equations that he kicked the ball 36 meters. You don't like it, but that's what happens. When I tried solving this without that information, you end up with all sorts of values that don't work. You have to pretend as though, oh, he kicked the ball 36 meters, and you base the time that you get off of this distance. I don't like that, but that's what happens. Oh, by the way, I'm wearing a dinosaur shirt riding an asteroid. It's kind of messed up, right? Too soon?
Too soon.
Too soon. Anyway, it's a Vsauce shirt. It comes with a Curiosity box. I get a bunch of them. And this is my science shirt collection. I think I've got like 10 of them now. And I just got a new one a couple days ago. So maybe we'll see that next week. You know, when I'm not in Chicago. By the way, I'll be in Chicago for a week doing AP training. So I'm going to try to make videos while I'm there to help you guys get through this. And also just maybe some fun videos of what's in Chicago. I hear there's Sears Tower is there, and there's like a glass floor you can stand on and see like hundreds or if not 1,000 feet above the ground. That sounds terrifying, but I want to do it. We'll go back to that. Anyway, back to problem 11. Okay, kicks the ball, 20 meters per second, 53. How much? All right, so my first instinct is to go to I want to know how high the ball went. How high is y? Right? Because y is up and down and x is horizontal. And we know that y has to do with gravity. Gravity is going to change the trajectory of the ball. So therefore, I'm going to start with y equals, I'll just write the whole fancy equation from the get-go. Change in y, change in distance, equals velocity initial times time. Remember, this is in the y, this initial velocity. Everything in this equation has to be in the y. You do have situations where you use x in this equation. That means you have an acceleration in the x. And we'll talk about that another time because we will have situations like that. But right now, gravity, this is a y equation. Minus 1/2 g t squared. Okay, remember, this is usually plus, but we make it minus because gravity is down. And you can tell if this is 3.505 meters high, then that's a plus, and that means anything going downward has to be negative for this to work. So 1/2 gt squared. All right, so how am I going to get the solution? I want to know how high it goes. Well, I can solve for time, and I could get the initial velocity. Okay, let's say if I got initial velocity, well, the problem is we'll have two unknowns, right? We'll have t as an unknown, and y is an unknown, and you don't want two unknowns in one equation. Okay, basic rule of math, two unknowns two equations. One unknown can work with one equation, but two unknowns, one equation. So let's do that. Well, what do I have? I have a distance, and I could break this speed into vectors, and I can get an x and a y value for my initial speed. So let's do that. Let's go, let's use the x component of 36. So that's x equals velocity times time, right? Well, what's x? It's 36. I said 36. And what's velocity? Now, the reason we can do this is because the time it takes for us to go this far is obviously the same time it's going to take us to go up and over. Okay, now the one thing I don't like is that we assume we can go 36 meters in the first place. Making that assumption means that we probably made it automatically. So I don't like that, but that's what we're dealing with here in this problem. Anyway, 36, v of x. Remember, this is v of y. So to find v of x, we're going to use our initial. We're going to do cosine of 53 times 20. Now, I explained to people a couple days ago, I'm going to take a little pause here from this problem. I'm going to explain why cosine is x, just really fast. So say we have the unit, say we have a circle, not the unit circle, we have a circle, and let's say this is 90 degrees. Actually, we don't need to say that. We know that, right? That if we have a line going this way, it's at 0 degrees, and we have a line going this way, it's at 90 degrees. Okay? If I take my calculator, let's take the cosine of both of those and see what we get. If we take the cosine of 90, we get 0. Okay? That means, this is a weird way of putting it, that means we have no cosine in the horizontal. If we're pointed straight up and down, we have nothing in this direction. 0. 0 going left and right. Right? Let's do the opposite. Let's do cosine of 1. Or sorry, cosine of 0, right? The 0 right here. And that will give us 1. You can think of that 1 as being 100%. That means cosine of 0 is 100% cosine. Or, as we think of it, 100% x. So when we get a vector that's like at an angle, we're actually figuring out sort of like the percentage or what fraction of this angle is in the x. And we do that by multiplying by cosine. Because when we multiply it by cosine of whatever this angle is, it automatically gives us only the piece in the x direction. Same thing happens with sine. If we click sine, you can probably guess already. If I take sine of 90, we get 1, or 100%. 1 is 100%, right? And if we try to take sine of 0, which is here, how much sine do we have in the 0? We have 0 sine in the 0. Okay? So that's why we do that. Okay. Let's go back to what we're doing over here. I just want to make sure everyone understands that piece if they didn't get it the first time around when we were teaching it. So I'm getting a percentage here of cosine of 53. So let's do that. Cosine of 53 gives me 0.60. You can think of that as being 60% of that 20 is in the x direction. So velocity in the x, what's 60% of 20? Well, we'll just multiply by 20. 0.6 times 20, 12.03. 12.03 of that 20 is only in the x. And the way you can think of this is if we added something that was 12.03 in one direction to something that is whatever we're going to get in the y direction, it would add up to 20. Now, it is not linear. We can't just go 12.03 minus 20 to find out the other one. Turns out it has to be a balance. And I'll show you what I mean here in a second. So v of y, which is up and down, is the sine of the same angle, 53. It's the leftover. That means, well, 79% of it's in the y. And that makes sense, right? Because we're higher than 45. 45 would be halfway. We're higher than 45, which means we're closer to 90. That means we have a bigger number. So 79.8% of 20. Oops. I actually erased the first thing. Sine of 53 gives us that times 20 gives us 15.97. Now once again, you see if we add 15 plus 12, we don't get 20. But if we add 15 up plus 12 right, that adds to 20 at this angle of 53 degrees. That's how it works. All right, so there we go. We got our two angles. Well, velocity of x is 12.03. we're going to plug it into our equation, remember, because back to what we're trying to get here. We're trying to figure out time so we can use it to solve the rest of this. Well, let's do 36. Let's bring our v of x over here, divided by 12.03 will give us time. So, it's obviously going to be like 3, right? 3 point something. Because 12 times 3 is 36. 36 divided by 12.03, 2.99. Okay, so we end up with 2.99 seconds. I recognize this number, so I know I'm on the right track. I know I'm doing this the right way now. All right, so now let's solve. Remember, the original problem is, hey, are we going to clear this bar up here, this 3.05 meter bar? And the next question will be, hey, are we clearing it on the way up or the way back down? And that'll be easy to solve as well. Now let's just plug and go. So initial velocity in the y, well, we got that over here, didn't we? 15.97 when we took that sine, right? So we'll go 15.97 times 2.99. That's this part right here. Gives us 47.75. That is if we had no acceleration. But because we have gravity, we have to add this other piece. So we have to minus, which makes sense we're minusing, right? We're going up, we're slowing down. So gravity is eating away at what we did. Minus 0.5, that's at 1/2, right? Times 9.81 times t squared. Well, 2.99 squared. Which is, should be about 9, right? Gives us, what did I do wrong here? 486. Let's try that one more time. I obviously did something wrong. Okay, v of y, 15.97, 7 times 2.99 equals 47.75 minus 0.5 times 9.81 times 2.99 squared gives us, there we go, 3.89. I don't know why that was different than that. So this means we cleared the bar at about 3.89 meters. Okay, this is a bigger number than that, meaning the ball went over here. Okay, and how much did it clear it by? Well, we'll just take this number and subtract it from what it is. Minus 3.05 gives us 0.84. We cleared it by 0.84 meters approximately. Okay, now the next question is, was it like this? Or was it like this? We cleared it. Well, that's actually a really easy problem to solve. And I actually accidentally found the solution trying to find this solution. Well, we did it before. So let's pretend we don't know anything. It's easy to do sometimes, right? Let's pretend we don't know anything at all. And let's set this to 3. Let's say, okay, we need to clear at 3. And time, let's say we don't know time. Actually, you know what? We'll cover this in class. This is a weird one. I don't want to drag us down time-wise on this. I've already spent too much time on it. So we'll go to problem 13. But it's on the way back down. And the reason is if you plug in just generic numbers in here for this without using the other information, you'll find that actually the point at the peak, so like let's say if we set y to, if we figure out how high it went using the height equation, which is this one, and we start at 0, you'll find that it actually reaches the peak way before 2.995 seconds. Actually, it's more like 1 point something seconds. So that means on the way back down, it had to have cleared the bar. But like I said, that's a very long-winded thing, and we have quite a few more problems to get through. But the biggest thing is we got the time, we got how much we cleared it by, and then it's on the way back down because if you look at the halfway point, you'll find that the halfway point's at a much lower time. All right. I am going to remember to put the question up there. We're going with question number 13 now. Okay. Question 13 goes as follows. A brick is thrown upward. Scandalous. A brick is thrown upward from the top of a building at an angle of 25 degrees. Well, let's draw our building. An angle, 25 degrees. What else? To the horizontal, that makes sense, with an initial speed of 15 meters per second. Cool. The brick is in flight for 3 seconds. How tall is the building? So it's in the air for 3 seconds. This one's a little tricky, if I remember, comes up, comes back down, hits the ground. Okay, so like I said, the question's asking, how tall is the building? Okay, the really way this one works is we'll find how long it takes to get to the halfway point. Okay, and the reason we do that is because we know that when we get here, the velocity has to be 0 in the y direction. We have some starting velocity. We'll figure out what that is using sine here in a moment. But when we get to the top, it has to be 0 because it turns around, right? So we use that information to actually help us solve this problem. And let me grab my notes. If not, I'll be sitting here thinking, and thinking on video is just not, it's just something that takes way too long. Okay. Looks like what I did is, the first thing I did is I decided, you know what, I want to find the vector components of this. And I made a list of everything I have, information-wise. So, velocity in the x is going to be equal to, I used a different color, that's all right. Velocity of x is going to be equal to the cosine of 25 degrees times 15. Remember, this is going to give us the percentage of 15 that's in the horizontal, in the back and forth. Okay, and then in the y direction, we're going to do the sine of 25 times 15. And that'll tell us the vertical speed. Only the vertical. No, I remember a lot of people ask me, like, well, why are we splitting it up in the first place? We know how fast it is. Well, because only in the y direction does gravity eat away at our speed, and in the x direction it doesn't. So by splitting them, you can figure out things of this one that you wouldn't be able to if they are merged together. You have to have them separate. All right, so cosine of 25 times 15 gives me 13.59. Okay, I'm gonna try to use a different color from now on for my for my solutions. 0.59, if I can remember, sine of 25 of 15, this is on the y, gives me 6.339. Remember, this is meters per second. This is our speeds. Okay, what's next? All right, I want to know our peak height. So to figure that, I say y final equals y initial plus, okay, you keep seeing this equation over and over again, right? Plus initial velocity in the y times time minus 1/2 at squared. Now, we are going to have, gt squared, right? Because it's gravity. We are going to have situations where we're adding this, not subtracting it, or we're adding two negatives, because if later on, when we get to the rest of the problem, as we're coming down, we're going to be adding our speed from one piece to another. Actually, I'm not sure if that's this problem. It will be in a problem where we'll do that, where we end up actually combining these two in a positive way instead of a negative way. You'll see why. All right, so let's pretend our starting position is 0. That's easy. This is our 0. Like I said, we're pretending this is actually its own little physics problem, and then we're going to use this solution to find this solution. So it's almost like we're solving two separate physics problems. Right now we're only worried about this. And the reason we only need to worry about this is because we can set something to 0, our velocity in the y, versus here. Okay, now initial velocity in the y isn't 0, right? Initial velocity in the y is this number right here, 6.339. So 6.339 t minus, well, 1/2 of g, you guys can remember, is 4.9 meters per second squared, t squared, and we don't know our final y yet, right? Okay, what did I do next? Well, I solved for t. How do I solve for t? Well, if I launch something up in the air, I know gravity's working against me, and it's an acceleration, and I know I have an equation. Now, I also have a change in velocity. Now I said I have a velocity initial here and a velocity final here. So I know, let's start with some basics here. I know that acceleration equals velocity times time, and if I can solve for these two, I can solve for time and use it in the equation I really want to use it in, right? Up here to find that height. So, remember, that's the whole point of this problem, is we're trying to find the height from here to here. But if I can find the height up here, and just pretend I'm dropping an object, I can actually subtract this height from this height to figure out, or sorry, I can subtract this height from this height to actually give me what this one is. And we're going to do that in a little bit. So A, I'm going to exchange for G, and V, which is 9.81, let's just write it in right now, 9.81, and then we take velocity, which is in the Y, 6.339, 6.339 t times t. It's getting a little messy here. But I'm going to divide this out to solve for t. And then we'll plug it in there. Alright, so 9.81 divided by 6.339 gives me 1.54. So that means it took 1.54 seconds to get from here to there. That doesn't seem right to me. Is that correct? That doesn't seem correct. Oh, that's because I'm doing it all backwards. Oh, let's back up, guys. The numbers are right. It's acceleration equals velocity over time. So what I did is I actually combined my distance formula. So that's, once again, that's 9.81, and velocity was 6.339. It's getting a little late. And I know if I want to solve for t, I need to switch these two. T equals that divided by 9.81. So it's just inversed. And so yeah, the time is actually a lot shorter than that. So I was like, that shouldn't take very long, and that should take a lot longer. And we know the total time is 3 seconds, right? So this is going to be some part of that 3 seconds. Which is kind of cool, because then we can figure out how long it took, how much time we have left, right? So 6.339, that's 6.339 divided by 9.81 gives us 0.646. So time is 0.646 seconds. Okay, cool. So we have a time now. Well, let's plug it into our y value. This will tell us how high we were above the ground. Okay, so wait, was this 6.339? Oh, that's velocity, yep. I'm seeing it again there. It's throwing me off. So 6.339 is our velocity times time. This is our, if we just were flying, this would be our speed, right? Our distance speed equation, but we have acceleration. We'll add that in a second. So 6.339 times 0.646 gives us, okay, that distance, 4.09. But then we have to subtract gravity from that, right? So minus, now keep in mind, we're probably going to get a negative number here because we're going down afterwards. 4.9 times t squared, which is times 0.646 squared, gives us 2.05. So the height here, just right here, I'll just do a little right here is 2.05 meters. We're going to save that information for right now. But we now know, the most important thing we know about this now is that to go that 2.05 meters, it took us 0.646 seconds. Okay, and why that's important is now we know how much time the total trip went. They told us that at the beginning. So if we take 3 minus that, that'll tell me how much time it took to hit the ground. And if you guys remember anything about what we did during the projectile motion stuff, like the marble, is if we have a time, we can find a height really easily. So let's do 3 minus 0.646, and that'll give us a time of this whole from up here to down here of 2.354 seconds. All right, cool. So what are we gonna do with that information? Well, we're gonna plug it into our equation for height again. So I'm just gonna write a bunch of stuff we don't need right now. There we go. There we go. There we go. Because remember, we're using all of this just to figure out how high this building was, right? Really complicated way. Let's get a tape measure, right? Really long tape measure. All right, so height is a y value because it's up and down, equals, same thing we keep doing over and over and over again. Velocity initial times time, or remember it's y final minus y initial, or I'll even go further back. It's delta y, right? Delta y equals VIT minus 1/2 AT squared. All right, now this is no longer y final, velocity final over here. This is a whole new problem just using this one piece of information. All that stuff we did is to get this and that little bit of height that we had at the beginning. So what I'm going to do is I'm going to restart, and I'm going to call this VI, V initial, and call this V final now. So now we're just worried about this area. Well, what's VI? I'm going to pretend VI is 0. Now I could say that this is actually my height I'm looking for, but then we had to make VF 0, and we're actually trying to find that, so we won't do that. If VI is 0, it doesn't make sense that our velocity is 0. Actually, we can't make this velocity 0. Never mind. Ignore what I said. Does it make sense that we make this 0? Well, as we're going up, right at that point of turnaround, there is no the ball, the whatever it is, the rock ball, whatever it is, stops moving for just a second, right? It goes, and then it drops. Not even a second, right? A moment, a millisecond, a microsecond. It goes. So VI can be considered to be 0. So we can get rid of it. Because remember, VI times T, if VI is 0, anything times 0 is 0. So we get rid of it. Delta Y. Let's break this down real fast. We have Y final minus Y initial. That's what delta Y means, right? Well, Y final is the value we're looking for, but we can pretend that Y initial is 0. Or we can flip it around and say this is 0, and that's a number. But let's say we call Y final 0. Okay, which makes sense because this is up is positive, down is negative. Then we get negative Y initial equals negative 1/2 AT squared. And if negative and negative, they go away. Now, if you're having trouble following along with this, just remember all this did was just simplify to Y equals 1/2 AT squared because we had no initial velocity. It just simplified. Okay, and remember A is still G, so let's fix this. 1/2 of G is 4.9. This is going to look really familiar. What are we solving for? We're solving for height. This is the equation. Do we have T? Yes, we do. It's right there. So let's do it. 4.9 times 2.354, went really far on that one, squared gives me 27.1 meters. And guess what? That's not the answer. Remember, that's the answer up here. We want to know it without this initial little push-up. We want to know the height of this building. So what we got to do is we just got to subtract that number from that number. So we got to subtract that from 2.05 just to figure out the height of the building. So we'll go minus 2.05, and that gives us 25.1. I think the book says 25. It rounds. That's okay. Not sure what I did with the cap to this pen. I'm sure we'll find it someday. Oh, it's in the other pocket. Never mind. All right. So that was problem 13. Let's look at problem 15. All right, problem 15. Let's do this. All right. So a car is parked on a cliff overlooking the ocean on an incline. So car is here, and there's an incline. So this is where the car is. I'll write C for car. And there's an incline and a cliff. All right. There's an angle here of 24 degrees, right? And below the horizontal, the negligent driver, jerk, leaves the car in neutral, and the emergency brakes are defective. Yeah, bad luck all around. The car rolls from rest down the incline with a constant acceleration of 4 meters per second squared. So there's an acceleration of 4 meters per second squared. For many of you, this might be the first time that you've used an acceleration that isn't gravity. Usually it's always gravity, right? For a distance of 50 meters. So this length right here, this is 50 meters. That's how fast it's going. That's the angle it's going at. All right. What's the question? A, we want to know the car's position relative to the base of the cliff when the car lands in the ocean. And then B, we want to know the length of time the car's in the air. So we want to know how long it takes to land in the water. And we want to know how far it went to go out there, right? All right. Oddly enough, I spent a lot of time solving this problem today, and then it turns out that I was making like one single algebra mistake over and over again, and that's the whole reason I had trouble solving it. So, first of all, I know right off the bat, I'm going to need to know what's going on right here. So I'm going to use all this information right here to figure out the x velocity and the y velocity, right? You can kind of tell that all this scenario, this setup, is to figure out what this is. If we can figure out what this is, then we can just simplify this into a simple projectile motion equation, right? Actually. Yeah. All right, let's do that. So first things first. What is my first thing I want to do? Well, there's two different ways of solving this, and I did both just to sort of prove to myself I was doing it the right way. Okay, the first thing I could do is I could use just the distance equals, which the distance is usually y. We usually say y equals v times t plus 1/2 at squared. But because I'm dealing with this angle, I decided to call y just some generic distance. This distance right here. Which we know that distance is in fact 50 meters. We know that we have no starting velocity at the beginning. Remember, this is always starting velocity. So this goes away. And we find that 1/2 at squared. And a is not 9.81. This situation is 4, right? Because we're dealing with some friction, we probably have some, we're not going down, we're not falling, we're falling at an angle. So we'll say 1/2 of 4 meters per second squared. Well, we all know that means 50 equals 2t squared. 50 divided by 2 gives us 25 equals t. And to get rid of the squared, we square root it, and we say t equals 5. Pretty simple. Okay, now there is a whole nother way to do this. This is how I did it the second time. The way I did it the first time is I went back and I actually used an equation that, where's my tail? You have that tail? Thanks, camera guy who's not actually here.
You're welcome.
There's another way to do it. And we haven't really had much use of this equation until now. And so I'm gonna use it this time just so we can see how it's done. We could also use this concept of v squared equals vi squared plus 2ax. Okay? And, well, let's see. Do we know all this information? Well, we're looking for the velocity here. Okay, well, do we have any starting velocity? No. The car, before it got sort of rolling down the hill, had no velocity. So this whole chunk goes away. And to get rid of the square, we're going to square root the sign. Okay, and remember, our acceleration was in fact 4. So 2 times 4. And our x is just a distance. And I don't like that it's x. It should be d in this situation, right? D. And our d is in fact 50. Well, 2 times 4 is 8. 8 times 50 is 400. And if we all know the square root of 400 is 20. Look, we got the exact same answer, right? So we could have used this method to have a time-independent equation, or we can always use the 1/2 at squared. But, oh, by the way, remember that other one we got 5, right? We got 5 seconds. I didn't get to the conclusion on that. We got to 5 seconds on that. Well, if we do 5 times, like we can go crazy. We can say 5 times the sine of 24 times 4. It turns out you'll actually get 20 from that as well. So we get the same answer using 2 different methods, which this told me really, really, really well that I was getting the right answer, that the velocity was in fact 20 meters per second. Like I said, there were some problems with this process, and it turns out to be one division problem towards the end that caused the whole problem. But one of the things I did is I tried both methods. That's how you use the equation. If you use the kinematic equation that I showed you at the beginning, y equals 1/2 at squared, and I said y was actually d in the situation, we would get 20 as well. We would take that time that we solved for, which was 5, plug it into there, and do time times velocity in the y, and we would get 20. So we get the same solution either way. Good. So there, we finally used that other equation, right? The whole point of this is that we found the initial velocity, So V equals, I'll write V total, Vt. Okay. The reason I'm doing that is because we do have an x and y component of this. Now, most of our situations where like we throw a rock or whatever, we have no y velocity. This time though, this is at an angle. And we all know this angle is 24 degrees. So, to figure out what's happening down here, we need to break this into its components. V of x equals 20 times, now remember we're going to get that percentage by doing the cosine of the angle, which is 24. Now you notice it is an angle downward. If you wanted to, you could take 360 degrees, subtract 24 from it, and you're going to get the same answer, but it's going to be negative because it's down. So really, there's no point in doing all that. I just like to use the angle from the horizontal, 24 degrees. Okay, 20 cosine 24. 20 times cosine 24 becomes 18.27. So 18.27, and V of y, same thing, but this time we're going to do the sine. 20 sine of 24 gives me 8.13. Cool. So we have two velocities now. We have V of x. I'm going to get rid of all the equations we just did and just stick with the answers here. V of x. It's like these little small. V of x, V of y. And that's at this point right there. Now it's just a general projectile motion equation. All right. So first question was, how far from the wall did it land? Well, if you remember the marble launch activity or anything like that, to find how far something went, we first have to worry about how long it took to fall. Then once we find out how long it took to fall, we can plug it into an x velocity equation to figure out its distance. Right now, how long did it take for it to fall? Well, let's do y initial. Oh, by the way, I think it said in the problem, but I didn't write it on here. This distance is actually 30 meters. As soon as it leaves the cliff, let's see. It falls for a distance of 50 meters to the edge of the cliff, which is 30 meters above the ocean. So this is 30 meters above the water, right? Cool. So we know our y. So we all know that that delta y equals velocity in the y initial times time minus 1/2 gravity times time squared equals its location, or equals the total distance it fell. Now, we can pretend this is 0 down here, so we can say y final is 0 minus y initial, which is 30. And we can say negative y initial. So, like I said, y final is 0, so we're just going to get rid of it. Then remember that delta y just became that y final minus y initial. Y initial equals velocity in the y. Now, usually we don't have any velocity, but this time we do. We have 8.13. So let's put that in there. 8.13 times time minus 1/2 of g, remember is 4.9, 9 t squared. So now we have one equation, two unknowns. So we're missing something. We need to figure out time before we can finish this whole process. And I actually, what did I do? I did something really interesting, but there's two ways of doing this as well. I think there's two ways of doing this, maybe not. That's right, this is what I did. I sat there and I said, okay, there's a problem with this. This is initial velocity, right? This is the velocity here. Well, I could use delta V equals, wow, my writing's way off. Delta V equals acceleration times time. Remember, acceleration is just gravity, right? Problem is, I have initial velocity. Remember, delta V just means V final minus V initial. I have initial, 8.13. But I do not have V final. So I still have two unknowns. That'll equal 9.81 times t. So I get to use that other equation again, the one that we haven't got to use very much before, right? I'll use a different color so we don't get it mixed up with everything else we have going now. Remember, I'm trying to figure out VF here. So I'm going to go back to that other equation. I'm going to say, okay, if I'm trying to find final velocity, I'll take it squared. It'll equal VI squared plus 2AX. Remember, X is just distance. I hate that it's an X. A times D, right? Because it's a vertical distance. It'll actually be Y in this situation. So we could say 2AY. Just remember that this last value is always just some distance, horizontal or vertical. Now, that A, of course, we know is G because it's falling. And 2 times gravity, 9.81 times 2, should equal like 19.6. Yep, 19.62. So this will become 19.62. And Y, we know, is 30 meters. So let's plug that in as well, right off the bat. Times 30 will give us 588.6. That's fine. 588.6. Cool. Initial velocity is 8.13. That's the speed that it left here as it comes down was 8.13. So we'll do 8.13 squared. And I'm going to add it to that other value. So an easy way to do that, let's do this. 8.13 squared plus, and I'm going to use that, plus, hit the wrong button here, the answer I got before, which was this. Gives me 654, so equals 654.6969. And now to find final velocity, I had to square root that to get rid of the square value, right? So what I'm going to do is I'm going to take the square root of the answer we got, and I'm going to get 25.5 as our final velocity. 25.5. Now remember, the whole reason we did all this whole reason we did this equation and all of this, so we can plug it back into here. So now we have V final minus V initial, which is 25.5 minus 8.13. So minus 8.13 gives me 17.45. 17.45 equals, well, that's 9.81. 81 times time. This is where I made my mistake earlier. I kept flipping these values. I don't know how I did it, but it kept happening. So if we divide by 9.81, we find that the time it took for this to fall was 1.78 seconds, approximately. Cool. Well, that gives us the time. That actually gives us the final solution. If we look at the last problem we had, the second part said, how long did it take? Going backwards, the first thing it said is, how far did it go? Well, the nice thing about this is once we know time, and we know how fast we are going in the horizontal, it just becomes x equals v times t. 18.27 times that number, so times 18.27, and we get x equals 32.5. There you go. That's the final answer. So this is part A, this is part B, this is problem 15. A little bit of extra here. We're using some acceleration to find our starting velocity, but I like this problem. This one will make me sad to erase because this is a good problem. Except for the fact that poor somebody left their car in neutral and it coasted off a cliff into the water. Good luck getting that back. Alright, problem 17. A little heads up, problem 19, we're going to skip. If you're waiting on this thing for problem 19, we made that video like a week ago. It's already on there. If you look at my YouTube channel, Scott's a Nerd, you'll find problem 19 completely solved. It's like a 25-minute video because it's the first one I ever did involving projectile motion. So I took it very, very, very slowly. This seems slow too, but not compared to that one. So if you want problem 19, different video. Okay, problem 17. This one's a bit shorter. Not too hard to solve, actually. A projectile is launched with an initial speed of 60 meters per second. So 60 meters per second. And 30 degrees. Thanks. Thanks, mysterious camera guy.
You're welcome.
Colby. 60 meters per second at an angle of 30 degrees above the horizontal. Is that what it says again? Above the horizontal. Yep, there it is. The projectile lands on a hillside 4 seconds later. Actually, I think I did this problem wrong earlier, so we'll see if this actually works out. It lands on a hillside. I pretended like it landed like right here. But I still know how to solve this problem. No worries there. The projectile lands on a hillside 4 seconds later. So just keep in mind that t equals 4. Now, when I saw this before, I pretended like this was actually down here and it was the same height. It says hillside, so that doesn't actually work. So we'll see if we can solve this live on camera the right way. What is the straight line distance from where the projectile was launched to where it's going? So this gets kind of complicated. What's the distance between here and over here? So one thing we need to know is first we need to know how far this is. Or we need to know how far this is. Because we got to figure out this angle. And after we figure out that angle, we got to figure out that distance. Or we got to figure out one of the other sides of this triangle right here. All right. So let's erase it. We get back to basics here. Okay, first things first. When I look at this problem, my first instinct is to say, okay, where's the halfway point? The reason I can once again use the halfway point is I can pretend velocity ends up being 0 at the halfway point, right? Let's do this. There's a couple different ways we can do this. We can do vf squared equals vi squared plus 2ay. And I can solve for y. And I can pretend that the final velocity is, in the horizontal, is 0. And so this would be 0. Now, I know like you're probably thinking, it's like, well, why doesn't that represent this? Well, because here the final velocity is not going to be 0. It's going to be some number, right? Okay, so let's figure out what this is. Vf squared, so Vf equals square root of 2. Well, remember, a is 9.81, which is gravity. Well, what's 9.81 times 2? I'll skip this part. It's 19.62 times the height. And final velocity. I did this backwards. It's VI. VI should backwards, guys. Sorry about that. It should have been square root of all that squared, right? We don't know this. We know all of this except for y. It's the final velocity that's in fact 0. So let's get rid of that. Rewind. Vf squared equals Vi squared plus 2ay in this situation. Okay, final velocity is 0, which means I want to move this over here, and it's going to become negative Vi squared equals 2ay. And I'm going to take the square root of that value. I hate the fact that it's a negative. We'll fix that later. That shouldn't be a square root of a negative ever. We'll figure out what happened there in a little bit later. I'm figuring, oh, you know what it is? It's because gravity's negative. So that will actually be a negative and a negative. We'll make them positive. Okay. World still works. Universe still works. 10.6. Okay, this number we can actually figure out. Remember, the square root of 19.6 is the same thing as saying square root of 19.6 times the square root of y. You can break things apart like that. The velocity initial in the y direction is going to be sine of 30 times 60. So remember, sine is the y value. So sine of 30 times 60 gives us 30. Hey, that's magical. Okay, 30. Well, what's the square root of, let's do 30 divided by the square root of 19.6. And actually, you know what? We'll square that to figure out what y is. I'm just going to skip a bunch of steps here. So let's do some brackets here. Let's complicate things. Try not to complicate things. 30 divided by the square root. Where is it? There it is. Square root of 19.6. Okay, 19.6 squared. 45.9. So it says y equals 45.9. Cool. That's a good value. Why not? All right, so 45.9 should be up there. Now, what is the time it took to get there? Because I want to start subtracting time here. So we know velocity, but we know that delta v, wow, I'm really messing this up. Delta v equals acceleration times time. Acceleration is 9.81. And we know that delta v is the change in velocity. We know velocity started at, where's that number we got before? It's not on here anymore. It's the sine of 30. Oh, it was 30, right? 30 times 60. Yeah, it ends up being 30. So it ends up being, it starts at 30. So that's, remember, delta v equals v final minus v initial, which ends up being 0 minus 30. Remember, gravity's negative. So we end up getting a negative 30 equals negative 9.81 times time. We'll take negative 30 divided by negative 9.81, and we'll get a positive 3.05. Now, why did we need to know that? Well, first of all, we know how high it is now, and we know the time it took. Right there. This whole first thing I did, I'm not sure we needed that actually. We'll see. We might. I think we do need that, but we'll make sure there in a moment that we actually did. All right. That's the height from here to there. All right. So t equals 3.05. And I might actually double check this number here in a moment, just in case. Now, it said the whole trip took 4 seconds, right? So that means from here to here, it took a time of 4 minus 3.05. Oops. 5. That should be what, 0.95? Yeah. So that means we still have 0.95 seconds left. Okay. With 0.95 seconds left, well, we can plug this right into our falling equation from here to figure out how far it fell. Well, let's see. Y equals 1/2 AT squared. A is g, gravity, so that becomes 4.9 again. 4.9, and t is 0.95. This should tell us how far it went, right? Remember, this is a negative number, so we should get a negative value over here, because gravity is negative, which makes sense, because we're starting from 0 here and going down negative at this point. All right, so 4.9 times 0.95 squared gives me a y value of 4.42 meters. Now that means we fell 4.42 meters, but we already know how long it is to get here. So if you take this value, the total, and subtract it from this value, we should get the height of the hill, which is what we're looking for here. So let's do 45.9 minus 4.42. As I'm not 100% about this number, but I'm pretty sure it's right. It says the hill is about 41.48 meters high. Let's check that in the text. This is the moment of truth. Did I embarrass myself on camera? 17. Was it 17? Yeah, it was. This says 52 meters. Oh wait, it wants to know the speed. Okay, am I looking at the right problem there? Oh, what is the projectile's velocity? What is the straight line distance? Oh, okay. So yeah, we haven't figured this out yet. So we do have a height here. Okay, I missed this stuff. If you guys remember, I'm actually looking for the distance from here to there, not this height. But this height will give me that distance right there. Where's my towel? All right, so let's erase all of this except for the time and the distance. Those are the important things we got out of all this. All right, actually, I shouldn't have erased that other distance. It was, okay, this is what we need. This is what we use to find this side of the triangle, right? The side of the triangle was 41 41.48 meters. What I need to do is I need to figure out this length of the triangle right here. Okay, so opposite of our hypotenuse. We don't know what this is what we need to know. So opposite of our hypotenuse is cosine. So I know if I take the cosine of 30, it should equal 41.48 over R. All we're going to do is switch these places to make this work. So it's going to be R equals the cosine, or 41.48, over the cosine of 30 times, that's it, yeah. So 41.48 divided by, bracket, cosine 30, and that's it. Let's see. That doesn't seem right. 47.89. This says that, I don't like that one bit. 41.48 divided by cosine of 30 gives me, okay, so I made a massive mistake here. You guys probably already figured out what it is. That distance is incorrect. And this is why. I use that df squared equation to find my height, and that doesn't work. We need to use, once again, y equals vi times t minus 1/2 at squared to solve for this y value, which is the height here. Okay, let's make it the same thing, then I'm going to be like, what? Alright, so let's rewind about 10 steps here. I need to refigure out what that height was. I did that incorrectly, I believe. It's okay. It's late. I've read like 20 some problems. I made a mistake here. It happens. So I'm going to do sine, to figure out the y, sine of 30 times 60 gives me 30. So this is 30. And the y times t, which is 0.95. 0.95. That number I trust, I think. This becomes 4.9 times 0.95 squared. Okay, so let's do this. 30 times 0.95 minus 4.9 times 0.95 squared equals syntax error. That's because we went the whole thing again. 30 times 0.95 minus 4.9 times 0.95 squared, close bracket, equals, okay, this says the height's actually 24. Right here. This is 24. 24.077. Okay. Is this y value? And that is, that is the time it takes for it to go from here to here. So this is actually the value here, 24.077. Is that right? No, that's the total height. My bad. That is the height here. 24.077. Alright, for this height, remember we had to pretend velocity initial was 0. Y equals 0 minus 4.9 times 0.95. Wow, I'm doing this way off, guys. I'm so sorry. I'm getting tired. 3.05. That stays the same. Alright. That number was wrong. It's supposed to be 3.05. We want the time from here to there. We want the height here. So 30 times 3.05. What was that other time again? 0.95? That still exists. Alright. We'll just keep those two numbers. It's 3.05. If I wasn't doing this in a marathon, I would just completely restart the video at this point, but it's okay. 30 times 3.05 equals 91.5 minus this part, 4.9 times 3.05 squared gives me 45.9. Okay, so this total height right here is 49 or 45.9 meters high. Cool. Now, to figure out this distance right here, we need to pretend this is our 0. So we're going to use the same equation, but instead we have no initial value. It's still 4.9, but now it's times that 0.95. Because remember, our total time is 4 seconds. That's how much time we have left. So we're going to subtract this number from what we get. 4.9 times 0.95 squared becomes 41.495. I feel like we're getting the same number. Using both methods, which means something is incorrect here. So that means this height is 41.495. Okay, that's cool and everything. So we've gotten the same number twice, I think. 41.495 for this height right here. So that's the first problem. How high is that hill? That's how high it is. What's the distance between our starting point and the top of that hill? That's the next problem we have here. All right, so let's do, once again, we know that the cosine of 30 is equal to opposite 41.495 over hypotenuse, which is r. And we know that when you just multiply over here, we divide by that, so we end up with r equals times the cosine of 30. Ooh, I think we're right. Okay, 41.495 divided by cosine of 30. 47.9. We get the same value again. Okay. Well, I'm doing something wrong here, or the book is incorrect. I'm getting a distance of 47.9. The book says we should get a distance of like 101. I don't know. Unless you're talking about the whole path, then maybe. So I might be just misreading this. It's okay. I won't hold this one against you if you get it wrong, because there's some issue going on here. All right. Like I said, we're skipping 19. Let's look at 21. 21 is actually a really short problem, and so is 23. We're on to our short problems, because these ones are in a new section, and they mostly have to do with your how you're observing something. Okay. I really don't like the fact that that problem is causing me so much trouble. It's such a simple thing. All right, topic 3. We're in number 21. There we go. Suppose a boat moves at 12 meters per second relative to the water. So we have some water. I remember this one. We have water. We have the ground. We have a boat that's moving this way at 12 meters per second. Okay, what's the next part? If the boat is in a river with the current directed east at 2.5 meters per second, so the water is in fact moving at 2.5 meters per second in the same direction as the boat. What is the boat's speed relative to the ground when it's heading east? Well, here's the ground. The ground's not moving, or at least it's not moving compared to these two things. If it's moving 12 meters per second and it's getting put in, it thinks the water's sitting still, that means it's 12 and it has that speed on top of it already, because someone looking out of the boat and the water would be like, oh, it's not moving. That's because you're moving with it. And in fact, the ground's not moving beneath that. So that should be 14.5 meters per second. And then I think the next scenario is, well, what if we do 12 meters per second in the opposite direction? Well, then it has the opposite effect. We're actually moving against the tide. So compared to the ground, we'd actually be moving at 9.5 meters per second. Just this minus that. Really simple problem. That's it. That's the whole problem. Compared to what we've been doing, this is like child's play, right? It's all relativity. Eventually, if you ever take AP2, we'll do special relativity. You'll understand why these perspectives are so important. But we're not there yet. Anyway, problem 23, last one I'm going to cover in this video. Okay. Okay, this one's a little different. The jet airliner is moving at 3 times 10 to the meters, or 3 times 10 to the second miles per hour east. So it's going this way at 3 times 10 to the second. Is it 3 or 30? What was it? Yeah, 3 times 10 to the second miles per hour that way. And this is sort of preparing us for the use of vectors at some point. And enters a region where the wind is blowing at 1 times 10 to the second miles per hour in a direction of 30 degrees north of east. So here's east. It's moving north of east by 30 degrees, which is what means this. 30 degrees. Okay, it's above that. And it says it's blowing at 1 times 10 to the second miles per hour. You guys all know that just means 100, right? 1 times 10 to the second is just 1 with 2 zeros. Alright, at 30 degrees. Alright. Find the components of the velocity of the jet airliner. Okay, this is pretty simple. So, velocity, just of this, of the jetliner, velocity of the x is equal to 3 times 10 to the second. And it says, I think it says relative to the ground. Relative, right, find the components of the velocity of the airliner relative to the air. Okay, so we write it this way. V of jet to air in the x. So it says jacks. Jet air in the x direction. 3 times 10 to the second, right? Because that's all in the x. What is it in the y? Well, there's nothing. There's nothing up and down because we're heading straight east here, right? So V jet air y j is equal to 0. Okay, that's A. We're done with part A. Part B. Find the components of the velocity of the air relative to the Earth. So now we're looking at this one, part B. Well, the air relative to the Earth is it's moving at it's moving at in the x direction. So V air Earth x. So it's like AEX here. There's a capital A for these. So we can tell that I'm not talking about acceleration. We're just talking about the air. Okay, so the air compared to the Earth is moving, well, there's an angle, but we know to make this an x, we have to do cosine. Cosine of 30 times that 100, it's almost like a percentage, right? Will give us 86.6. All right? Yep. 86.6 miles per hour. Remember that's in the x direction. And V, air compared to Earth in the y direction is sine of 30, because remember sine is our y value, times that same 100, and that gives us exactly 50 miles per hour when you do that. And that's in the y. Cool. So these are the vectors based on Earth, or was it air compared to the jet, air compared to the Earth, and I think in part C, it's a combination. You combine them, you add them together to figure out what the jet's doing. I said, you guys actually done problems like this before if you're in my class, but we don't break it down in such simple ways. We actually already should know how to combine vectors like this. So let's see, 23. Part C. Write an equation analogous to 3.11. Don't worry about that. For the velocities. So we want velocity of jet to air and velocity of air to Earth to figure out velocity of jet to Earth. Okay. So to do that, we're going to do velocity of jet to air, so compare the jet to the air, is equal to velocity of jet to the earth minus velocity, I believe, what's the last piece? Yeah, jet of the air. Now you might have written it the other way. You might have said the velocity of jet to the air plus the velocity of the jet. Did I do that right? Sorry, feels like we're using the same number twice, and I don't like that. Let's see. Oh, sorry. So this is say AE at the end of here. I was like, that doesn't make sense. Air to the earth. Now, the way I originally would have written this myself, actually in the question it calls for jet to air using the other two, but I have actually written it velocity of jet of the air plus the velocity of the air to the earth equals the velocity of the jet to the earth. Because this feels more like a vector we would use in a real problem. So we'd say, okay, what's our total velocities in the x and y here? We're going to add them to our total velocities in the x and y here. These are vectors, right? And that'll give us our where is it moving compared to the earth. We've done problems like this before in this class. Part D is, well, we're actually going to do that. We're going to plug in all the values. I'm not going to go through the whole process because I said we're right at the end here. We'll end up getting, I'll just put the values in, we'll end up getting 3.9 times 10 to the second. As like I said, if you combined, if you took the velocity of jet of the earth, which is not even up here, but if we plug in the values we do know in these equations, we should get 3.9 times 10 to the second. And then if we took the, we did trig and we figured out the angle on that, we should get 7.36 degrees north of east. Okay. Well, guys, that is a lot of physics, and Scott's a nerd. I'll see you guys later, and hopefully get a nap.